Hello, good morning. Okay, so today we will have two examples of the topic methods of proving. So I have selected some of the questions. So these two questions are from the homework 2, which I have just sent to you during the weekend. So we are going to talk about how to solve two questions, and then if you want to solve it by yourself, then you may have a pause and then think about it and then check if you can solve it using a similar way. Notice that for these questions there can be more than one proof. So in that case, it is perfect if you can find the proof of your own. So let me introduce the two questions today. So the first one is question number 1 in homework 2. In this question, we want to show if n is a perfect square, then n plus 2 is not a perfect square. So perfect square is a number which can be expressed as the square of an integer. So if n is some integer square, then we want to show that n plus 2 cannot be some integer square plus 2. So there are many ways to solve it. So I will show two of them. So there are two ways that we are going to see. So the first one is, okay, so we will talk about this question later. And then the next question here is question number 11 in homework 2. And for this question, we are considering the equation z to the power 13 minus z to the power 2 minus 15015 is equal to 0. We want to show that for this particular equation, there is no integral root, which means that there is no integer z such that after plugging z into the equation, it becomes correct. So this is part A. And similarly, in part B, we want to show something more. We want to show that there is no rational root. So in that case, for any rational number, it cannot be fit as z in the above equation. Okay, so we will talk about these two questions. So for the first one, so this is the first one. N is a perfect square, then n plus 2 cannot be a perfect square. So the direct proof method is like this. So in a direct proof, what we want to show, okay, so this is a statement of the form something implies something, P implies Q. So if we want to do direct proof, we assume P is true and then hope that we can derive Q is true in the end. So we assume that n is a perfect square, and in the end, we want to show that n plus 2 cannot be a perfect square. Okay? So first of all, suppose that n is a perfect square, then at this point, we can see that n cannot be equal to 0 because n plus 2 in this case will be equal to 2, and then 2 is not a perfect square. So at this moment, we can rule out the case that n is equal to 0. So we will consider all the cases where n is greater than 0. Okay? So in such a case, then we can safely assume that n is equal to p squared for some positive integer p. Yeah, because n is a perfect square, so it is not 0. So it must be some integer square. So we can just ignore all the negative integers, right? So we can focus on all the positive integers. So now, at this point, this is the condition, P implies Q. The first part, we assume that n is a perfect square, and then what we get is n is equal to p squared for some positive integer p. Now, the next observation that we can see is that if there is a perfect square which is greater than n, then it must be at least p plus 1 whole square. Yeah, because p is already an integer, right? So the next perfect square, or the other perfect squares that are larger than it, must come from some integer p plus 1 or larger to the power 2. So any perfect square greater than n has to be at least p plus 1 whole square, at least. And then p plus 1 whole square, it turns out that it is equal to p squared plus 2p plus 1. And recall that p squared, this part is equal to n, and the remaining part is 2 times p plus 1, so it is at least 2 because p is a positive integer. So p is at least 1. Okay, so 2p plus 1 is strictly greater than 2. So what does it mean? It means that any perfect square must be at least p plus 1 square, and it must be strictly greater than n plus 2. So in that case, n plus 2 cannot be a perfect square. Okay, so this is how we can show this question by a direct proof method. Okay, so we can also try the other way. So let's try an indirect proof. So this time, let us show this result by using proof by contradiction. Okay, so if you want to show the result using proof by contradiction, so it is the target here. So the target here is to show that the negation of what we want to show will lead to a contradiction. Okay, so this is the blue part is the original thing that we want to show. By using proof by contradiction, we want to show the negation of this part will lead to a contradiction. So what is the negation of this part? This is P implies Q. This is of the form P implies Q. So the negation of this one will be something like we want to show that when this is true, then it is the fourth part of this one. So the fourth case of this one is P and not Q. So the negation of this whole thing, the negation of this whole thing is actually this one. So we want to show that n is a perfect square and at the same time n plus 2 is a perfect square. So this is the negation of the original statement. We want to show that this will lead to a contradiction. Okay? So let's see. Okay. Now notice that there can be many different ways of showing things. So we just give you some example so you can design your own proof as long as every argument that you write down makes sense. Okay? Now this is the proof that we use today. So here we assume what? So we want to show that this will lead to a contradiction. So we assume that this is correct. This whole thing is correct. And then in the end, something wrong will occur. Okay, so we assume that this is correct. So n is a perfect square. N plus 2 is also a perfect square. So n is equal to p squared for some integer p. And then n plus 2 is equal to q squared for some integer q. Okay. Now, we have an observation. So n and n plus 2, they are perfect square, right? So, but then the difference between them is 2. And 2 is an even number. So what does that mean? So it means that P and Q must have the same parity. So what is meant by same parity? It means that either both of them are odd or both of them are even. We cannot have one of them even, one of them odd. Because if one of them is even and one of them is odd, then in that case, the difference must be an odd number, so it can't be 2. Is that okay? So P and Q must be of the same parity. Now, in that case, we start from this one. So n plus 2 minus n is equal to 2. So it is equal to q squared minus p squared. Is that okay? Now, q squared minus p squared, you can decompose it as q plus p multiplied with q minus p. Now, notice that these numbers, they are of the same parity. So p and q are of the same parity. So in that case, q plus p must be an even number. And also q minus p must also be an even number. Is that okay? And then q and p cannot be the same. So in that case, q plus p and q minus p, they are both even numbers and they cannot be 0. So they are at least 2 here. So q plus p multiplied with q minus p will be at least 4 here, at least 2 times 2. So it is at least 4. So from the second part here, so I'm skipping some of the arguments here. So in a formal proof, we need to write it down. But here, for demonstration purpose, so I'm explaining this using words, using verbal. But then we will see that q plus p is at least 2, q minus p is at least 2, so 2 times 2 is at least 4. Okay? Now, at this moment, we get a contradiction. What is a contradiction? We get something that is always wrong. 2 is greater than or equal to 4. This is something that is nonsense. 2 cannot be greater than or equal to 4. So what does that mean? So it means that if we start with our assumption here, if we assume that the statement that we want to show is wrong at the beginning, we get something wrong in the end. So in that sense, it means that the statement, the original statement that we want to show must be correct. Because if it is wrong, then we get something wrong. So it can't be wrong. Okay, so this is the answer for question number 1. Now for question 11, so we want to consider the equation, this one, z to the power 13 minus z squared minus this number is equal to 0. And we want to show that there is no integral root, and moreover, there is no rational root. Now, if you can see, an integer must be a rational number. So in that case, if we can show part B, then we don't need to show part A. So in that case, so if you can show part B first, then there is actually no need to show part A. But then perhaps part A will be something that is easier to show because part A is more restricted. So part A talks about something that is even more special. So in that case, we have more information about the root itself, so we may be able to prove it more easily. And then the knowledge of A may help us to show why B is correct. Okay, so let's see part A. Okay, so there is no integral root. And then we are going to show this by using the method prove by cases. So in particular, we can ask ourselves 2 questions. The first one is, can the number z be an odd integer? And the second one is, can the number z be an even integer? So let's go back to this one. Can z be odd? Now, if z is odd, then z to the power 13 is an odd number, multiply itself 13 times, so it must be an odd number. Odd times odd is odd. Okay, so this is an odd number if z is odd, and this is also an odd number if z is odd, and this is already an odd number if z is odd. So odd minus odd will be even, and then even minus odd will be odd. So in that case, it cannot be 0. So what does that mean? When we check that whether z can be an odd number, we will find that it cannot be an odd number. It is because this part is an odd number. And it cannot be 0 because 0 is even. Okay? So we see that this shares something that is similar to the previous question. We are checking the parity of, we're making use of the odd-even parity of the equation here. Okay, so the next case is we want to check whether z can be an even number. So whether z, this here, can be even. Now if z is even, then even times even is even. So even to the power 13 will be even. Even to the power 2 will be even. So this equation will then becomes z is even. So in that case, even minus even is even, and then even minus odd will be odd. So again, it cannot be 0 because 0 is even. Odd cannot be 0. Okay? So in that case, what do we have? So we find that z cannot be odd. And at the same time, z cannot be even. So we find that no matter z is odd or z is even, this equation do not have z as a root. So in that case, for all the integers that we can consider, this integer cannot be a root of the equation. So in that case, we have shown part A. Okay, now how about part B? Okay, so part B, it says that there is no rational root. So what we are going to show, okay? Now, actually, part B, if you have already studied a theorem called rational root theorem, then maybe you can use it directly to solve this. But then we don't need to have the knowledge of this advanced theorem. We can just show this by using the same trick again. So we are going to show this by using proof by contradiction, and then we are going to make use of the idea or the result of part A. Okay. So here we start by using proof by contradiction. So we assume that there is a rational root for this equation. So if there is a rational root, so we let Z to be equal to P divided by Q be a rational root. So I'm a little bit lazy here. The P and Q here are both integers. So let Z be the ratio of two integers PQ, and then let this Z be a rational root. Now again, we can assume without loss of generality that P and Q do not have any common factor. So if P and Q, they have common factors, then in that case, we divide the common factor from P and Q at the same time so that we make another pair of integers PQ without any common factor. And we use this one instead of the original PQ. Okay, now P and Q do not have common factor. So now we plug in Z is equal to P over Q in the original equation. So we have P over Q to the power 13 minus P over Q to the power 2 minus 15015. It is equal to 0. So in that case, we will have what? We will have P over Q to the power 13. So we plug in Z there and then multiply the equation by Q to the power 13 and we will get this as a result. Okay, we will get something like P to the power 13 minus P squared Q to the power 11 minus 15015 times Q to the power 13 is equal to 0. Now, what do we have? Okay, so we can check the cases. Can P and Q be both odd? Now, if P and Q be both odd, then we have something wrong here, because if PQ are both odd, then this is odd minus odd minus odd. This part can be an odd number only, so it cannot be 0. So we find that PQ cannot be both odd. Now, on the other hand, if one of the PQ, if exactly one of the PQ is even, so let's say P even, Q odd, what will happen? P even, Q odd, we will have even minus odd, and then this part cannot be an even number. Okay, so it cannot be equal to 0. So P even, Q odd cannot happen. Now, how about P odd, Q even? Now, if P is odd, Q is even, then this is odd minus even minus even. And then again, this part will be an odd number, so it cannot be 0. So P odd, Q even cannot happen. Then the only case that we can have is P even, Q even. P even, Q even. So we have even minus even, so it can be even. But for this case, we will have a contradiction, because when P and Q, they are both even, then they will have common factor. They will have a common factor 2. So in that case, we will lead to a contradiction. So what does that mean? So if we assume that Z is equal to P over Q to be a root, a rational root, then no matter P is odd or even, Q is odd or even, we cannot make the original equation correct. So if we start with Z is a rational root, we will always lead to something always wrong. So what does that mean? So it means that there is no rational root. Is that okay? So I hope you find this example easy, and then this is going to strengthen your understanding about proof by contradiction. And then so I think that's all for what I want to show today. And then there are new types of questions in this assignment 2, which requires some further understanding of the topics that is going to be covered this week. So please check the video for this week, and then see if you can finish the whole assignment 2 quickly. Okay, so thanks all for coming. I'm sorry for the delay today. And then let's meet again on Wednesday. See you. Thank you very much. Okay. Do we need to prove why P and Q have the same parity? This is a good question. Yes. So somehow, you mean for the first part, question number one? Yes. Yeah. We need to argue. So if they don't have the same parity, there is something wrong. Yeah. Okay. Thank you very much. Okay.